Hello everyone. Instead of taking live class, I thought of recording the video and sharing it with you via YouTube. So this will help you to see the recorded video any number of times at your convenience. Okay, so let's start. I've already sent you this experiment number one PDF in the WhatsApp. Uh, so let's do it. So we'll start with this experiment. Here we'll learn few basic commands how to execute them in Matlab. Okay, so as the title says, getting started with Matlab. To get familiar with Matlab commands and their uses in analysis and design of a controller. So in this lab, we are basically going to learn how to design a controller and how to define its stability. So in the later class also, we will discuss about stability. We will design a controller and we'll see whether that system is stable or unstable. So first of all, we'll learn how to write a transfer function in Matlab. Okay. Now everything is mentioned in this. So what you need to do, you need to go through this document and just repeat it in Matlab software. Okay. So if you have Matlab with you, it's very okay. If you don't have, just follow me. I'll show exactly what will be done in Matlab, and after writing those commands, what are the outputs we are going to get. So just follow. So it's very easy. So we start with writing transfer function in Matlab. Then we'll see the step response, the time response of that transfer function, and then we'll learn how to draw both plot and root lookup of a transfer function. Okay. And the transfer function is nothing but a skeleton of a module. So okay, we are going to build up a um, model or a controller. So this is a skeleton. The transfer function will be the skeleton where we are going to give some inputs and we are going to see what are the outputs it is giving. Okay, so out of those outputs we can analyze whether the system is stable, unstable. That means how well our system will going to run in practical. So this is a simulation software. So let's start. So the software tool required is Matlab 2000 or higher. Okay. So first thing first, how to write transfer function in Matlab. There are three ways to define a transfer function in Matlab. So we have mentioned all these three, but we are going to use this second one, which is very easy and convenient. But you are encouraged to try all of this. So let's start. Let me open Matlab. So the Matlab we have in the lab is Matlab 2014. So once you open Matlab, you are going to see these two basic windows. One is command window, and that is workspace. Command window is basically the output window. If you write program, the output will be shown over here. And the workspace is for variable and all, so which we are going to learn in later classes. The first thing we need to do, we need to open a new script where we are going to write our program. So upon click on that new script, we can see that editor Untitled 2 has opened where we are going to write our program. Okay, so here we are going to write our program. Here we are going to see the output, and whatever variable we are defining over here, it is going to show in the workspace. Let's see the first command. To define transfer function, what we need to do, we can use either of these three. We are going to use this one. Here we are defining s as a transfer function first. So the command is s equals to tf in braces quote unquote s. So let us type this. So s equals to tf should be all in small letters. So s equals to tf quote unquote s. So this way we have defined it. Now you can take any transfer function as an example. So in the assignment we have given few, you can try all of those. So let's take an example. Let's take a transfer function. Okay, you can choose any of these. So let's define a system and then give some variable to it and define the transfer function. Okay, so let's go to Matlab. Now as is defined, so as will be taken as a transfer function. So let's define our system. You can give any arbitrary name. So we are taking system1 as our transfer function name. So this name is arbitrary. Okay, you can choose anything. You can give your name also. Now to define that, let's in the right hand side we need to write the transfer function 100 by s cube s cube plus 5s square. Now 5s square, you can't write 5s square like this. It will show error because after 5 s square is in product form, means 5 and s square are in product form, so in between you have to place a multiplication sign, otherwise Matlab will show error. So 5s square plus 6s. Now 6s also should be written in this manner, 6 multiple sign, then s, 6s plus 10. Okay, let's press enter. We go to the next one. Now to check whether this transfer function is correct or not, we can run this and we are going to see the output in this command window. Okay, let me save it. Experiment number 1. So there was some problem in naming it, like we can give space in the name. So instead of space, I use a underscore sign. Now it is working. See, system1 has been defined in this way. So it's a continuous time transfer function. Now there is a catch over here. See, in the program, if you finish this line with semicolon, then the output is subtract. Means for that line you are not going to see the output. Like in the first line, see after this I have concluded this line with a semicolon. That is why the output of that statement is not appeared over here in the command window. So let's try this. Let me remove this semicolon and try it once again. Run it. See now, as we have defined as a transfer function, it is also shown in the output, and the second line as usual same. Now if you suppress this with semicolon and if you press run, you are going to see that for this statement the output will not come or will not appear in the command window. See, it's not appear. So this is a catch. If you need to suppress a particular output, you can do this with semicolon. As we don't want this one to be displayed in the workspace, I've chosen it to be separated with semicolon. Okay. So our transfer function is defined. So this way we have successfully written a transfer function. So now the next step is to see its time response. With time, how would it how would it how do its waveform we can see using step command. The command is also written over here. So you can see there are two commands. One is step, another is step info. In the braces, there will be the system name which you have given. So this name is arbitrary. So in braces, the transfer function name will be arbitrary. Whatever transfer function you choose, just apply that name over here, and it will be done. So let's try all these two. So let's try stf step. Now our variable name or transfer function name is system1. Now let's run it. In the background it is running. Oh, okay. See, this is its time response. Okay. Now from here we can see the overshoot, undershoot, settling time, everything. Okay. So if you want all these data in the graph, you can just right click on it. In the characteristics, you can choose anything. Say peak response, it will show you the peak response. If you take the cursor to this point, it will show you. See the peak amplitude, overshoot percentage, and the particular time, 2.37%, 2.36. This way you can choose settling time, rise time, steady state, everything. Now regarding all this, it will be covered in the theory class, like what is overshoot and all. If you have learned already, then it's fine. If you haven't learned, it will be covered in the theory class. Okay, so don't worry, it will be covered by Bhowmik sir. So this is how we are going to see this thing. Now this is in graphical form. If you want all these value in numerical form, there is another command. So let me close it for now. So step is giving this, the graph form. Now if you type step info, and in the braces if you name the system1, you are going to get those values in. Now I'm leaving it. I'm not closing it with semicolon. If I close it with semicolon, then it won't appear in the command window. As simple as that. So let me run. Okay. So this is the first thing. This is for the step command. So graph format will not be suppressed. That means, see, I have closed this with semicolon, but even it is closed with semicolon, it will come again. As long as the statement is there in your program, it will come. Okay, so that is why it is coming. If I press run, it will come. Okay, now step info is, see, you can see this value. As I run it uh, 2 times, it appears 2 times. If I close it with semicolon, it is not going to appear. See, only the graphical format change. So this way you are going to get those values also. Okay, so this is the step command. Now let's check the next command. The next command is bode command. What it will do, if you type bode and in the braces if you name the system, you are going to get the bode plot of the frequency response of that particular transfer function. Now what is bode plot? Bode plot is a tool by which we can judge whether a system is stable or not. In details it will be covered in theory class, but I'll give some basic idea about it right now only. So let's type that command first, then we'll see what it does. So the command is bode. Now system s system1. Okay, now run it. So actually bode plot maps the frequency response of the system to two graphs. So in the plot itself, single plot, we are going to get two graphs. Okay, one is magnitude versus frequency, another is phase versus frequency. Okay. See, in the x-axis we have frequency. Okay, so frequency is common to both the graphs. So these two graphs together is known as bode plot. So in bode plot, what we get, the frequency response of the system through two graphs. The first one, where magnitude and frequency is there, it is known as magnitude plot or bode magnitude plot. Okay, so it expresses the magnitude of that transfer function in decibel. So decibel is a special unit, so not like sound. Okay, it's dB. I'll talk about it also in within few seconds or few minutes. So next plot is phase plot. Okay, in the phase plot, y-axis will have phase in degrees and frequency in the x-axis. So frequency is common to both the plot. Now the thing we are going to find from both plot are two variables, are two not variables, two terms or two tools. Those tools are known as phase margin and gain margin. So I repeat, phase margin and gain margin. Gain margin will find from magnitude plot. Okay. So this will what magnitude gives? It gives us the gain or the magnitude of the system. Okay. But the unit is different, dB. Okay. And in the phase plot, we are going to find the phase margin. Okay. So this phase margin and gain margin are the tools by which we can judge whether the system is stable or not. Ideally, for a stable system, both the phase margin and gain margin should be positive, or phase margin should be greater than the gain margin. Okay. Now let me show you how we can find manually the phase margin and gain margin from a bode plot. Then I'll show you how to find it from the Matlab directly. Now on the plot, let's check how to find those margins. Let me enable the grid first so that I can scale it well. Okay. So to find phase margin and gain margin, we need to know about two terms. The first term is phase crossover frequency. Another one is gain crossover frequency. As I said earlier, from the magnitude plot, we are going to find phase margin, gain margin. Okay. And from the phase plot, we are going to find phase margin. Now, these two are interrelated. Means these two graphs complement each other. Like to find gain margin, we need to find phase crossover frequency from this, and to find gain margin, we need to find no, as I said, to find gain margin, we need to find phase of crossover frequency first, and then to find phase margin, we need to know gain crossover frequency. Okay. So let's first find gain margin from this plot, magnitude plot. Now to find gain margin, first of all, we need to find phase crossover frequency. Now what is phase crossover frequency? To find phase crossover frequency, we need to come to this phase plot, where we need to check whether this plot is cutting the minus 180 degree line. See, you can, this is minus 180 degree line. Okay. Now we need to check for the point where this curve cut this. I think this is the point. This is the point where it is cutting or going to. I think this is the point. Okay. So this is the point where uh, the phase plot is cutting minus 180 degree line. Now this frequency is known as phase crossover frequency. Now we can easily check the frequency. It is 2.44. So let's note it down. I hope you have pen and paper with you. So note it down. So our phase crossover frequency comes out to be 2.44. Okay, it's 2.44 radian per second. Fine. Now, with the help of phase crossover frequency, we are going to find gain margin from the magnitude plot. So now that we have found phase of crossover frequency, it is 2.44. Now you have to check for that 2.44 frequency or radian per second frequency in the magnitude plot. Let's find it. Okay, if you move the cursor, you can find the frequency is changing because in the x-axis frequency is common. Okay, so we are going to go for 2.44. Oh, so we got it over here. Okay, so this is 2.44 frequency point. Now at this point, whatever is the magnitude is known as gain. Okay, remember this is not gain margin. We are yet to find gain margin. So at phase crossover frequency, whatever magnitude we are getting, this is known as gain. Okay, so the gain we are getting over here is 1.4. No, it's 14 dB, 14 decibel. So note it down again. Okay, note it down again. So let's see. So what we have found so far, we have found phase crossover frequency. Frequency. The value is 2.44 radian per second. Now at this frequency, at phase crossover frequency, the gain, let me turn it with capital G, the gain is 14 dB. Okay, so this is what we have found so far. Now how to find gain margin from this value? The formula for gain margin, let me give a short name to it, GM. So GM is, the formula is 0 0 minus G. Okay, so gain margin will be 0 minus G. From 0 dB line, we have to subtract the gain and we are going to get the gain margin. So it will come like this, as we have found gain as 14. So 0 minus 14, it will be minus 14 dB. So this will be our gain margin. So as we can see, gain margin GM is actually negative of gain. GM is negative of gain. So the formula for gain margin is this. Okay, formula for gain margin is this: 0 minus G. Gain margin GM is equal to 0 minus G. What is G? The gain at the phase crossover frequency. Okay, so it comes out to be the gain margin will always be negative of G. Okay. Now from the plot also you can find the gain will be this length, from 0 to this, from 0 to this, from the 0 dB line, the point 2.44 of this gain plot, that length will be your gain margin. So it is a gain, the gain margin will be 0 minus V value. So gain margin is negative of gain. What is gain? The magnitude at phase crossover frequency. So we have successfully found the gain margin. The gain margin has come minus 49, minus 14 dB. Okay, so let's go to the second plot and find phase margin. Okay, to find phase margin, what we need to do, we need to find gain crossover frequency. As I already said, these two plots complement each other. To find phase crossover frequency, now we have found phase crossover frequency to find gain margin. Now to find phase margin, we have to find gain crossover frequency. So what is gain crossover frequency? It is that frequency at which the magnitude plot cuts 0 dB line. Now see, this is magnitude plot. Now this is 0 dB line. Find for the intersection point. I guess this is that value. This is that value. So it comes out to be like this 4.39. Okay. So this will be our gain crossover frequency. So what is gain crossover frequency? It is that frequency at which the magnitude plot starts 0 dB line. Okay, so it comes out to be 4.39. So let's note it down. Now, how to find phase margin? Now, at gain crossover frequency, whatever is your phase is known as phase lag. Okay, so whatever is your phase in the phase plot is known as phase lag. So let's find the phase lag first. So it's 4.39. Let's find for 4.39 frequency over here. So and the cut in the right direction. This is I think 4.38. So okay, 4.39. So at 4.39, the value of this phase plot is known as phase lag. Okay, so this phase lag is found as minus 214 dB. Okay, okay. So let's check for phase margin. Now whatever the values we have found, so this was up to gain margin. Now for phase margin, first we have found gain crossover frequency. The gain crossover frequency, the frequency is that frequency at which the gain plot cuts 0 dB line. Frequency. What was that value? We have noted it's 4.39 radian per second. Now at the gain crossover frequency, the phase lag we have found, phase lag. Phase lag is the phase at the gain crossover frequency. So let us define this value with phi. Okay, so phi symbol is not available in notepad, so I am writing it in letters. So phi comes out to be minus 214 degrees. Okay. Now, what is phase margin? How to find phase margin from phase lag? It is again a simple formula. Phase margin. Let me give it a short name, PM, not Prime Minister. Phase margin. Okay. So PM will be, the formula is phi minus 180 degree, because the line was minus 180 degree. See, this is minus 180 degree, so we have to subtract this phase minus 180 degree from the phase lag to find phase margin. So this is minus 180 degree which we need to subtract from the phase lag. So we are writing phi minus minus of minus 180. So this will come out to be phi plus 180. Now this one thing to note, this phase lag will always be negative. Will always be negative. Right? It will always be negative. As you can see from the graph, it is always under 0, so the value will be negative. Now let us find our phase margin. So we have got phase lag as minus 214, so add 180 to it, so we are going to get 214 minus 180, it will be 334, so it will be minus 34 degree. Okay, minus 34 degree. So this way we can find phase margin and phase margin. Now one more thing, how to convert this dB value to amplitude form. That means how much is 14 decibel or how much is minus 14 decibel. Let me show you how to convert it. Suppose you have 15 dB and we need to convert it into magnitude form. That means in amplitude form, not in dB. So 15 dB is how much in magnitude or how much in amplitude. So I'm taking a simple example. Say 15 dB, 15 dB is equals to x in amplitude. Okay. Now the conversion formula is like this. We need to convert this uh, decibel scale into normal amplitude scale. The formula will be like this. 15 is the decibel, so you write 15 in the LHS, give equals to 10. Actually basically log scale conversion, it will be 20 log, so its base will be always 10. Okay, its base will be always 10. So 20 log, then in bracket we put the amplitude value. So as we have taken x as that value, so we have written 50 is equal to 20 log x. So x will be the equivalent amplitude of 15 dB. We can find it easily from this relation. Okay. So in our case it was minus 14 dB. Okay. So we can write it like this. So this is the conversion formula you can use for any. Okay. Let's find for our is minus 14. So put minus 14 in the LHS equals to 20 log base 10, and in the braces we will put x. Now solve for x and we will get solve for x and we will get the amplitude of minus 40. Okay, so it is easy, it's not that tough. It will be what if I take log x, let's make log x as subject, log x is subject, so it will be 14 by 20. That means it will be uh, 1.47, 1.4 by 2 will be 1.452, that will be 0.7, I guess, 0.7. Okay, now should be minus 0.7. So what will be x? Now if we take 10 to the power in both sides, log will be cancelled and we will find or x. X will be, if we take 10 power 10 to the power in both sides, we get this will comes out to be 10 to the power minus 0, 10 to the power minus 0.7. So let me find the calculator. So what is x? 10 to the power 10 to the power minus 0.7. So this will be, the value will be almost 2. It's 0.1195. So here, or x, that means gain margin in amplitude will be almost to 0. Point, what we got, 0.199, like this, some value 0.1995, almost 2. Okay, so this was it. Okay. So you can note down whatever I have written in this notepad. Now, so this was the way to find manually page margin and gain margin from any board plot. Now you need not to do this in Matlab because they have commands or they have option over here. Like in the board plot, if you right click on this, you see this characteristic. Now if you click on this all stability margin, it will show you the values. Okay, now this is the gain, and the gain margin you can find over here. See, it is showing minus 14. Okay, so we also found this minus 14. We chose phase crossover frequency to be 2.44, so that it is exactly, almost exactly same, 2.45. And let's see the gain crossover frequency. Gain crossover frequency we found 4 point, we took 4.39, they have taken 4.36, so almost same. So the phase margin they got is minus 33, we got minus 34, minus 33.3 they got. See, you can see the value. Phase margin they got minus 33.3, we have got manually 34. Okay, so almost same. So this way you can find from Matlab. Okay, so this is from the board plot itself. There is again one command where we can get numerical values on those phase margin and gain margin. Like in step info, we got those numerical values. So we have command for gain margin and change margin also. So the command will be like this. In the third bracket, you type gn comma p small n. So the command you should be very precise. It should be capital G small m and comma capital P capital N equals to margin for which system? System 1. This 1, and we are done. Now if you run, see, the gain margin is almost 0.2 and the phase margin is minus 33.3430. So we can get those values also. Okay, so we are almost done with this. Only one command is left, that is, I think, root locus. So our locus system, so let's try that also. Hope you've got some idea about board plot. So this was basic board plot idea. So let's type this command and find root locus. Root locus in details will be covered in next classes. So in this class we are going to just type this command and we'll see whether how the curve looks like or the plot looks like. So let's type the command r locus. So there is one mistake. In this. So please edit it. It should be small letter r. Okay. It should be small letter r. So while typing I did some mistakes, so please correct it. It should be small letter R. So R locus, and type that system name again. This one. Okay, just run it. So this is the root locus. Okay, so here we can find poles, zeros, and all, everything which will be covered in the future classes as well as in the theory classes. Also, our lecture will explain it. So this was our first experiment. So what you will do out of this lab, you have to write this laboratory assignment for all these systems. Whatever I have done, you just need to repeat for all these systems. And also you are encouraged to find answer of this and write it in your copies. Okay, now once you have finished writing your lab copy or lab file, you have to take a snap and make a file. So it's easy to take snap and make a complete file. With PDF, you can make a PDF file by combining all those images and send it uh, in the send us to in the provided email. Okay, so we'll provide the email ID where you will find your assignment, lab assignment, so that we can give marks on your experiment. Okay, so it is mandatory that you would write this in pen and paper mode. So don't copy paste. Okay, you have to write in pen and paper. Okay, no soft copy will be allowed. So write it in pen and paper, then take a snap, merge it, make a PDF file, and then submit it. So hope you have understood this experiment